So now we're looking at the second of operators that can operate on a vector field and provide information about the behavior of that vector field. So if we're given, and it's the divergence, so given it F as P times unit I plus Q times unit vector J plus R times unit vector K, the divergence of a vector field is, so this is the kind of shorthand verbal description of divergence, but what does it really mean? It really means that we're taking the gradient operator again, like we did with curl, and we're doing a dot product rather than a cross product with that vector field. So and keep in mind that our gradient operator is partial x, partial with respect to y, and partial with respect to z. So let's go ahead and see how this performs, or how this works on a vector field. So I've got two vector fields here, and notice that since it was a dot product, this partial with respect to z may or may not be applicable. If I look at F, I can do the divergence of F with or without knowing that implicit there is a 0k. So let's go ahead and take a look at the divergence of F. So here's the vector field F that we were given, and we want to find the divergence. So we're going to do divergence of F, which is gradient operator dot product with F, which means we have the partial with respect to x, partial with respect to y, and partial with respect to z, dot product with cosine xy, sine yz, and 0. So that means I'm going to take the partial with respect to x of cosine xy, doing my dot product, plus, now I'm going to take the partial with respect to y, of sine yz, and then I'm doing a partial with respect to z of my z component, but my z component is 0. So go ahead and find these partial derivatives. In my first term, partial with respect to x is going to give me negative y sine of xy. If I use the chain rule, derivative of cosine is sine xy, and then partial inside x, partial of xy with respect to x gives me a y. And I think I said negative. If I didn't, then I should have. Plus, then partial with respect to y, derivative of a sine is cosine. Leave the argument alone, but partial derivative inside my sine function with respect to y is going to give me a z. So I'm going to have cosine of yz as my second term. And partial of 0 with respect to z is actually just 0. So the divergence of this vector field is that quantity. And then if I had a specific point x, y, z, I could evaluate the divergence at that point. So we were also asked to find the divergence of G, so let's go ahead and do that. So divergence of vector field G is gradient dot product with G. So I'm going to have the partial with respect to x, partial with respect to y, partial with respect to z, dot product with 2xyz, x squared z, and x squared y. When I do those partial derivatives and that dot product, partial with respect to x of 2xyz is going to give me 2yz, plus partial with respect to y of x squared z. There is no y, so that would be 0. Then partial with respect to z of x squared y. Again, x squared y is constant with respect to z, so that's another 0. So this divergence would be 2yz. So just another moment on why we're interested in divergence. It's also associated with fluid flow. So it provides important information. It represents the velocity of a fluid. So it could be a fluid. Gas is a fluid. If F represents that velocity, then the divergence represents the net rate of change with respect to time of the mass of fluid flowing from a point per unit of time. So that sounds kind of complicated on the surface, but if we think about it more simply, the divergence of F measures the tendency of fluid to diverge from a point. So, or we could think about a flux per unit of volume at that point. So, for example, if I have the divergence of a vector field at a point P naught, and I find out that that is in fact a positive quantity, what does that mean? Well, that means that the mass flowing out at the point P naught is increasing, or the net flow is outward, and P is considered a source. So let me go ahead and get that written down. Now, we could also have it be the case that the divergence of my vector field at P naught is negative. And so what does that mean? Well, instead of our mass flowing outward, our mass is flowing inward. And so our point, rather than being a source, is a sink. So let me go ahead and get that down for you. So if the divergence of my vector field at a point is positive, we know it's a source. If it's negative, we know that it's a sink. But what does a divergence at a point equal to 0 mean? Well, it really means that there is 0 net flow. So whatever's flowing in is balanced by what's flowing out. There's no net increase or decrease. And so in that situation, we say that the vector field is incompressible. And so you may have some experience with the ideas of sources and sinks. Probably a sink is more familiar to you as most computer chips, because of the electricity required to run them and the power consumption become sources of heat. And so most computer chips do have what's called a sink built into the chip to absorb the heat generated.